Section 4.7 is another one of those sections where we don't have any new material that we have to learn. We just want to apply what we know to new problems. And in 4.7, we're going to try to optimize things. Optimizing means we're going to try to find the best solutions. So in terms of our problems, we want to find minimums or maximums of different things. The basic outline throughout all of these problems is really the same. We need to read the problem a couple times in order to understand what's going on. As we're reading it, we're going to draw a diagram and put variables in place of unknowns and things that can, quantities that can change, kind of similar to related rates. We will clearly express what we are trying to maximize or minimize. The equation that we're trying to maximize or minimize is called the primary equation, and any other equations that we have which limit what we can do are called constraints or secondary equations. And we will start off with an example. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? So the situation is we have a river like so, and then we want to build a fence next to the river. We need to put fencing on 3 of these 4 sides. But how we build the fence, if we want it more tall and skinny or more wide and flat, is kind of going to be up to us. So the length and the width would be 2 different variables that we have in our problem. Let's read the question again. A farmer has 2,400 feet of fencing. Okay, so the 2,400 feet of fencing is a constraint, and that constraint is that 2L plus W adds up to 2,400. Okay, continuing on. 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fencing along the river. What are the dimensions of the field that has the largest area? So we want to try to maximize area. In terms of the problem that we just drew, our area equation is length times width. Anytime we want to find a maximum or a minimum, we can locate those at either the endpoints of the domain of the function or at the critical values where we have mins or maxes of our derivative. So we need to pay attention to the domain, and then we need a function that we can take a derivative of. Notice that this is an equation with 2 variables, 2 independent variables, so it seems. What we need to do is we need to write A in terms of just 1 variable so that we can take a derivative and find a critical value and do a number line to find the maximum. So that's where our constraint or our secondary equation comes in. We can rearrange the secondary equation to be W is equal to 2,400 minus 2L, and then substitute back into our area equation. A equals L times 2,400 minus 2L. Now we have something that we can take a derivative of, and we won't have to worry about product rules if we do a little bit of algebra here. 2,400L minus 2L squared. Now we recognize this is a parabola opening down, so it should have a maximum. So A prime, taking the derivative with respect to L, we have 2,400 minus for L. We can factor, and we get 600 minus L inside here. Then find our critical values as usual, and that gives us L equals 600. Okay, since L equals 600, that's a critical value. We can use our number line and our min-max techniques to determine if this is a max. So here is 600. Now, our equation is all in terms of L, and we need to pay attention to the domain of L. I'm sorry, the domain of A, that is, what values of L are allowed. Since L is a length of this thing, the smallest value for L that we could use would be 0. It wouldn't make sense to make the length negative. And then, again, if we look up here, the largest value of L that we could use, notice that there are 2 L's in the diagram, so the largest L we could use would be 1200, since we need to go out and back. That is, an L of 1200 would mean a W of 0, and that would use up all of our fence because of the 2L right there. We could actually, since these values are not critical values, we could use these values as test values in our first derivative. Nothing bad would happen. And if I do use 0, you'll get 4 times 600 is a positive number, which means we have an increasing area function here. And then if I pick something large over here, anything larger than 600 will give me 4 times a negative number, which is a negative number, and decreasing over here. So what do we see? We see there is a max of area when L is 600. Let's read the question again to make sure we have what we want. What are the dimensions of the field that has the largest area? So we have half of the answer. We have the length. The other dimension that we need is the width. If we scroll back up, we have an equation for the length and the width. If the length is 600, then the width would have to be 2400 minus 2L. L is 1200, W is 1200. And that gives us the solution of the problem.